Hello and welcome to my presentation, a study on deep face restoration models. My name is Keris Prisk. My final project, I opted for the paper, A Survey of Deep Face Restoration, Denoise, Super Resolution, Deblur, Artifact Removal. This paper gave a comprehensive overview on deep face restoration models and techniques. Using this as a starting point, I researched further developments in deep face restoration, since this was published in November 2022. In this presentation, I'll summarize my report by giving an introduction to what deep face restoration is, with an overview of the models and architecture commonly used. I'll then introduce the models I selected to trial and go through my demonstration. So what is deep face restoration? It's a field within machine learning and computer vision that uses neural networks to improve the quality of facial images. Unlike image enhancement, which aims to improve the visual quality of an image to make it more appealing, for example, changing the contrast or altering the exposure, image restoration aims to restore the image's visual quality to its original state. Face restoration is a specific application that requires knowledge of structural characteristics. There are a variety of causes for image degradation, with remedial action generally summarized as face denoising, which involves the removal of noise, for example, camera shake, face deblurring, to remove blur, for example, motion of the subject, face super resolution, to enhance low-quality images, for example, zoomed-in images or old images, face artifact removal, to recover quality lost during file compressions, and blind face restoration, which is a combination of the above, as is likely to occur with real-world images. There are three additional forms of deep face restoration which are out of scope for this project. Color restoration restores color to images, face and painting fills in missing areas of images, and AI-generated images can also use deep face restoration to enhance realism in the image. There are four main frameworks for deep face restoration models. The diagram from the initial paper shows the development of these frameworks over the last several years. Convolutional neural networks use layers of convolutional filters to capture and learn patterns in images with increasing levels of detail. These enable the model to learn the structures of facial features, to fill in missing details or correct blur or noise. They use windows to analyze portions of an image, which is a strength for image classification problems, where invariance isn't an issue, that can lead to reduced performance in face restoration, where longer range dependencies may be needed. Generative adversarial networks are made up of a generator network and a competing discriminator network. The generator creates images based on the real images, which are then evaluated blinded by the discriminator, which then predicts whether it thinks the image is real or generated. This is then fed back to the generator, and this iterative process is used to learn the features of the images. This allows GANs to learn realistic textures and details, which can be particularly useful in restoring low-quality images. The nature of the adversarial training means that generators can become overly focused with a particular subset of samples and generate similar images, leading to overconfidence in the discriminator. This is known as mode collapse and can cause generated images to exhibit similar features. Vision transformers, or VITs, are a new addition to deep face restoration. They make use of the transformer architecture, which is widely used in natural language processing, to learn sequential and contextual relations between words. In NLP, they use attention mechanisms to ensure context isn't lost across longer sentences, by learning which words are more important and therefore require a higher weighting. In image restoration, this methodology means VITs can learn how to optimize weights for different parts of the image to capture the context of the full image. This provides a big improvement over CNNs, which can't monitor long-term dependencies, but they are far more computationally intensive and more susceptible to overfitting. Diffusion models are the latest addition to deep face restoration. They use a class of likelihood-based models that learn the reverse process of well-defined stochastic processes. Information is progressively removed to allow the model to simplify the target distribution as a simple Gaussian distribution. They then use the reverse process to generate data from a given distribution. The combination of forward and reverse diffusion to learn the relationships between the data and corresponding noise distributions means these models are well suited to restoration issues where information is missing due to compression losses. They can provide very high quality outputs, but are very computationally intensive and difficult to train. Deep face restoration has additional complexity to traditional image restoration due to the specific facial structure. To account for this, some models use prior knowledge of facial structures. This can lead to improved accuracy, but can be affected by issues such as the angle of the face. Models that use geometric priors use methods such as facial landmarks, heat maps, and passing maps to determine geometric and spatial characteristics of the face. Whilst geometric prior methods involve using dictionaries, of individual faces. Reference priors combine these with specific dictionaries that combine high-quality and low-quality images of the same individual to learn how the facial mapping is affected by the reduction in quality. This can lead to improved accuracy, but is limited to cases where specific references are available. As previously explained, GANs are particularly good at learning realistic textures and details. Some models use pre-trained GANs in their architecture to improve handling of these features through latent mapping to balance quality and fidelity of the image. Non-prior-based methods focus on learning direct mappings from low-quality to high-quality images without relying on predefined facial information. Removing this dependency can reduce the computational intensity required, but can impact accuracy. The first of the selected models is the VQFR model. This combines CNN with a vector quantized dictionary and a parallel decoder. It encodes the input images to compact latent representations before enhancing them with high-quality codes from the vector quantized dictionary. A texture warp module uses a CNN to combine the input features and texture features to mitigate fidelity issues with the texture features. This approach combines the strengths of dictionary-based methods and GANs without relying on geometric or GAN priors. The objective of this architecture, shown in the diagram here, is to optimize both quality and fidelity. The GFP-GAN model combines a degradation removal module with a pre-trained GAN as a prior. It maps degraded images to close latent codes, which then guide generation of the high-quality facial details. Adversarial and identity-preserving losses are combined to train the model to optimize both appearance and identity. The CodeFormer model uses a transformer-based network to predict the most appropriate code mappings from a learned codebook. As shown in this diagram, a discrete codebook is used to map the high-quality encoder and high-quality decoder. The transformer architecture is then used alongside the low-quality encoder to determine the most likely mapping from the codebook for the high-quality decoder to produce an optimized image. This achieves a balance between quality and fidelity. The final model is the DifFace model, which uses a diffusion model to overcome the issues in deepface restoration, where models are provided with input images that have complex degradations outside of their training data. It constructs a posterior distribution for the high-quality output from the provided low-quality image. A pre-trained diffusion model is used as an intermediary to guide the construction, as shown in the diagram. I'll now show a demonstration of these models in Google Colab. To run this notebook, all that needs to be done is for the requirements file to be uploaded. An inputs folder has to be created, which can be done with this cell here, with the test image then uploaded. I've already run the requirements file to save time. Please note this warning message here. There has been a recent change in the code that means you may need to run this cell twice, but it will then work. I'm now going to set it to run all the cells. So we import all the required libraries. I've then printed my environment spec. So if you have any issues, you can see what I was using to hopefully be able to then fix the issue and recreate the code. Then go through loading each of the models from Git. I then take my input image and I modify it so that we can test the different forms of restoration. And then generate these modified images, which have been created in this folder here. I then run each of the models using those input images. I then plot these images showing the baseline image, my modified version, and then each of the 4 models. Each of these corresponds to one of the facial restoration methods discussed in the slides. So with the blind face restoration, the face artifact removal, the face to blurring, the face to noising, and the face super resolution. I then calculate some scores to quantify the performance of each of the models. Given this is a single sample test, these aren't overly reliable, but they give an indication of how the model performance could be analysed. I then have decided that for me, I think that the CodeFormer model performs best. So I've chosen to do an extra demonstration showing some more examples. You can then come here and choose the files to use. Here are the outputs, which show the restoration of some different images using CodeFormer. I've then looked at the folders of the specific face areas that it creates in the outputs, cropped faces and restored faces to show the detail of what it does. These really clearly show the improvements to the images. And this shows how much fun you can have with restoring old images. So here's just a couple of images I wanted to include. So the initial plan for this study was to retrain models on X-ray data, but this became unfeasible due to computational and time constraints. Whilst some models are trained on specifics of facial structures, others have no prior knowledge, so the ability to learn facial structures could be applied to learn skeletal structures. The most variation for this came due to quality issues surrounding veterinary X-rays. It is far harder to keep animals still during X-rays than humans, with the result being that animals are often anaesthetized for X-rays. This carries health risks, particularly with rabbits or elderly animals. Whilst it wouldn't be possible to correct for all motion issues, the use of image restoration in veterinary X-rays may be able to reduce the need for X-rays under general anaesthetic. It could also be used in human X-rays to help mitigate issues from exposure. In November 2022, the American College of Radiology announced there were 200 FDA-approved radiology AI algorithms ready for use. The image here shows an X-ray enhanced using GE Healthcare's Helix model. An additional use case I was interested in exploring was to enhance CCTV images for forensic analysis. In the UK, there are strict regulations providing enhancement of footage to prosecute a perpetrator, but the technology could still be used to help track the last known movements of a victim or to help identify potential witnesses. The adoption of VIT and diffusion-based models for image restoration is relatively recent, suggesting potential for significant advancements ahead. The capacity of these technologies to enhance low-quality photos and videos holds substantial commercial appeal, particularly in industries dealing with historical documents and images. There's an appreciable financial incentive for improving these techniques, particularly with a growing demand for restoring AI-generated images to enhance realism. This interest is likely to fuel further optimization and application of these innovative restoration methods. Thank you for listening to my presentation on deep face restoration models.